Yes, sir.
We are starting.
Yes, sir.
Yeah. So, good morning, Mushrif sir, once again, and good morning, dear participants.
Good morning.
Good morning. Okay. So, dear participants, we are in day 4, session 1. We are beginning. I welcome you for this day 4, session 1 of 1 week online mode faculty development program on recent trends and applications in biomedical signal and image processing, sponsored by AICTE Training and Learning, popularly named as ATAL Academy, AICTE New Delhi. We have gone through 3 days, 8 sessions, in which we have gone through very wide spectrum of trends and applications in biomedical signal and image processing, right from yesterday, if you are able to recall, data-driven Ayurveda to deep learning and then other things as such. Today, this session 1 will be delivered by one of the eminent professor again of the Yashwantrao College of Engineering, Nagpur, Dr. Mushrif. We will be talking on, wait 1 minute. We will be talking on brain MRI data analysis. Professor Mushrif, he is professor of ENTC department in Yashwantrao College of Engineering, Nagpur. I welcome you, sir, once again. Professor Mushrif has received his BE in electrical engineering and ME in electrical engineering from Balchan College of Engineering, Sangli, and then PhD from IIT Kharagpur. He is having 27+ years of experience in the teaching field. Presently, he is working as a professor in Department of ENTC Engineering, Yashwantrao College of Engineering. His research areas are computer vision, image processing, and machine learning. He has particular interest in the algorithms for medical image analysis. His work in these areas has resulted in over 50+ publications in reputed journals and conferences. In addition to this, he has served as a program committee to various national and international conferences on image processing. With his vast teaching experience of over 27+ years, his PhD from IIT Kharagpur in the field of image processing, and is further carried out in the and continuing his research in computer vision, image processing, and machine learning. I hope his session will be very much useful to all the participants who take away in their respective institutes either teaching things for their students or maybe as a research input for carrying out their research. I welcome you on behalf of all participants, sir, once again, and I am thankful to you on behalf of all of us, on behalf of GHRC as such, to readily accept our invitation and being a part of this 1 week FDP, which is sponsored by AICTE. Now I am making you, sir, presenter. You can proceed with your presentation. With all modesty, I request Professor Mushrif to start his presentation, start his session. Presenter now?
Okay. Good morning, all the participants. Good morning, Dr. Khanapurkar, sir, Dr. Akant, madam. And first of all, I thank you for giving me opportunity to deliver a talk. Today, I will talk on brain MRI image analysis. Actually, this was the work carried out by one of my PhD scholars, Dr. Yogita Dubey. So, I will be presenting you that work in today's talk. So, this is the outline of my talk today. So, I will introduce a little bit about MRI imaging technique, followed by that classification of brain MR images, then skull stripping and segmentation. So in this work, I will focus on segmentation techniques basically, where we have used the soft computing approach for segmentation. So basically, two types of algorithms we have developed. One is in thresholding. So we have developed two soft computing approaches for thresholding, segmentation using thresholding, and then in clustering techniques, that is fuzzy series clustering techniques, we have developed again two algorithms based on soft computing approach. So we have developed these algorithms based on rough set theory and intuitionistic fuzzy set approach. So now I know that the participants in this FDP are from various backgrounds. So I will try to cover the fundamental things and avoid complicated mathematical in this presentation. Okay. So magnetic resonance imaging is a very popular imaging technology nowadays. There are other technologies also like PET and PET scanning and CT scanning. But as compared to MRI imaging, these are the invasive techniques, because in the other techniques, for example, in CT scanning, the patient is exposed to the radio frequencies. He is exposed to the X-rays, right? As compared to that, MRI imaging is a non-invasive technique, and we can produce three-dimensional detailed anatomical images using MRI imaging techniques. Basically, these techniques are suitable for disease detection, diagnosis, and the treatment monitoring of the patients. So let us first understand how MRI technique works. So these MRIs employ powerful magnets which produce strong magnetic field. And when the body of the patient is exposed to these strong magnetic fields, the abundant protons in our body part, they come under this powerful magnetic field, and these protons they themselves spin, and therefore they produce their own field. But when these protons are exposed to this magnetic field, strong magnetic field, these protons get aligned with this magnetic force, and then these protons are given the radio frequency current, which is pulsed through the patients, and because of this, these protons get stimulated, and they spin out of their equilibrium, and after some time, this radio frequency current is turned off, and therefore these protons again try to realign with the magnetic field, and in this process, these protons release energy, and now different body parts take different times to get realigned with the magnetic field. So the amount of energy released by these protons and the time which the different body parts take to get realigned with the magnetic field. So based on this information, the MR image is constructed. So this is how the MRI technique works. Okay. So this MRI technique is basically more suited for non-bony parts or soft tissues of the body. So this technique is suitable for brain, for spinal cord, for nerves, for ligaments, and so on. So whenever these body parts are to be analyzed, then doctors prefer the other techniques such as X-rays or CT scan over the. So MRI techniques are more preferred by the doctors. And in the brain, we will be focusing basically on the brain MRI image analysis. So in the brain, MRI can differentiate between the white matter and gray matter. And MRI techniques can also be used for diagnosing the tumors. So basically, we'll consider two types of images obtained through the MRI scan. One is T1 weighted image. So in case of T1 weighted image, the magnetization is allowed to recover before measuring MR signal by changing the repetition time. And T2 weighted technique is one in which magnetization is allowed to decay before measuring the MR signal by changing echo time. So basically we'll consider these two types of images obtained through MRI. There are several other types also. So T1 weighted images are useful for assessing cerebral cortex, identifying fatty tissues, characterizing focal liver lesions, and so on. Whereas T2 weighted images are useful for detecting edema, inflammation, and revealing white matter lesions. So for brain MRI image analysis, T2 weighted images are more stable, but T1 weighted images are also used for brain MRI image analysis. So the two images, T1 weighted and T2 weighted images are shown here. The samples are shown here. Now these brain MRI images so obtained using the technique that we discussed, they are normally very low contrast images, and they are corrupted by random noise arising during the image acquisition process. So they are low contrast, and there is always a noise which occurs due to the image acquisition process. And then the RF pulses are given, so they also cause some kind of inhomogeneity. Inhomogeneity means there will not be uniform intensity in the image from one end to another end. So these MRI images are low contrast images. They are corrupted by some random noise, and there is also inhomogeneity. And due to this, there are various challenges in analyzing these MRI images. So, before applying any algorithm or analysis algorithm, pre-processing is very much required. So, pre-processing is one of the fundamental tasks required in before we go for the further analysis. So in pre-processing, basically our aim is to reduce the effect of random noise and go for the correction of the inhomogeneity. So there are many techniques used for intensity inhomogeneity correction and denoising. So basically for inhomogeneity correction, the FCM clustering methods are used. So FCM clustering methods, there are several variants of this clustering known as modified FCM clusterings. There are some model-based techniques, deformable model-based techniques, and there are many other generalized FCM methods. So many techniques are available for intensity inhomogeneity correction. And for denoising, some local filters are used, anisotropic diffusion filters are used, or some violet-based techniques are used. So you will find all these techniques in the literature. Now in today's talk, we'll basically focus on the classification of the MRI images as normal and abnormal images. Then we'll mainly discuss various segmentation methods and the quantitative analysis of the experimental results that we obtain. And so basically we'll focus on these two techniques. Then in this work we have used three different data sets. So data set 1, which are basically T2 weighted images, which we have obtained from the Lata Mangeshkar Hospital. Then we have also obtained some images from Sanjay Gandhi Postgraduate Institute of Medical Sciences, Lucknow. So that is our data set 2. And in data set 3, we are using the synthetic T1 weighted or simulated T1 weighted MR images from brainwave. So these brainwave images are the ground truth or benchmark images, you can say. So we have compared our algorithms with the benchmark images. So in T1 weighted simulated brain images, images with noise varying from 0 to 13% are available, and intensity inhomogeneity varying from 0 to 60% are available. So for classification of brain MRI images as normal and abnormal images, we have used a cosine modulated wavelet transform algorithm basically. So you can see two block diagrams. One is for training the classifier, and another is for testing the results. So in the training phase, from the MRI images, first we go for pre-processing, which reduces the noise and tries to eliminate the inhomogeneity, and then we use cosine modulated wavelet transform to decompose this image in 7 subbands. So 2-level decomposition is used, and then from these subbands we extract features. Basically we extract energy features. So that is a training phase. So these so whatever images we have selected for training phase, we extract features of all those images and store those features in the database. And then for testing also, the first 3 blocks are common. MRI image is first of all pre-processed, then cosine modulated wavelet transform is applied, then features are extracted, and then these features are compared with the features stored in the database, and a classifier is used which gives the result as whether the testing image is abnormal or normal. So the reason for using cosine modulated wavelets is that their ability to have better discrimination and low design implementation. So they are computationally less complex, and we get better features and more accurate classification results if we use cosine modulated wavelets rather than using the standard normally used wavelets as Dobishi's wavelets, dB4 or dB2 and so on. So in the block diagram, the filter bank used for extracting the subbands is shown. So it's a two-level decomposition. So after two-level decomposition, we get 7 subbands. The prototype filter is H0, it is a low-pass filter, and the analysis filter is a high-pass filter. This filter is derived from the prototype filter H0 itself by cosine modulation. So you can see here that Hi of n is cos of 3 pi by 4 into n minus capital N minus 1 by 2 minus pi by 4. So this is multiplied by H0. So the analysis filters are cosine modulates of the prototype filter. So here only 2 filters are used, one low pass and another high pass filter. So this high pass filter is derived from the prototype low pass filter by this cosine modulation. And after two-level decomposition, we get 7 subbands, the original image, and then these are the 2 subbands after first level decomposition, and after second level decomposition we get 4 more subbands. So in all we get 7 subbands. For all the 7 subbands we calculate the energy. Okay, so that forms our feature vector. So a feature vector consists of 7 features. These are all energy features obtained from the 7 subbands. So in a training phase, we extract all these features for all the images in the training set and store these features in our database. And the classifier we use for classification is a base classifier. So a very simple basic classifier is used for classification. The data set we used in this case is T2-weighted real human brain images which are obtained from the Lata Mangeshkar Hospital. The images were of 300 by 400 size. Total we had 40 images, 20 normal, 20 abnormal images. So out of these 40 images, we selected 14 images for training and 26 images for testing. So this size of training and testing images, training data sets, we arrived through experimentation. So this optimum for training was 14 images and 26 images were kept for testing. So these are the samples of normal and abnormal images. So you can see that in normal image, the basically there are say 3 different parts in this normal image. One is called as gray matter, another is called as white matter, and the space between this gray matter and white matter is called as CSF, cerebrospinal fluid. So you can clearly see that three different segments in a normal image. And the second case is the abnormal image. Here you can see that this portion, the gray matter portion, is little bit distorted. You can see a white portion in the gray matter portion. So this is a distorted portion. So this must be a tumor, and therefore we call this as abnormal image. Okay. So in this classification technique, we used 14 images for training and 26 images for testing, and so we got 100% classification accuracy. There were 20 means 13 normal images and 13 abnormal images in the testing case. So we got 100% classification accuracy, and we compared these results with the DT4 wavelet analysis, and where in case of normal images we got 100% classification accuracy, but in case of abnormal images the classification accuracy was about 85% only. So that is the first part of our analysis. Our main focus is on the segmentation of the brain MRI images. So in order to segment these brain MRI images, we need some pre-processing. So one thing is removal of noise and reducing the inhomogeneity effect, and before that we need to remove this skull. So you can see that there is a sort of ring at the outer boundary. So that is called as skull, and this is not useful for segmentation or further analysis. So before applying the segmentation algorithms, we need to remove this portion. That is called as skull stripping. So in this skull portion, there are extracranial tissues, meninges, then blood vessels are also unwanted. So all these portions of the brain MR image are removed in the skull stripping algorithm. And after the skull stripping algorithm, basically only three types of tissues remain in the image, which are called as gray matter, white matter, and cerebrospinal fluids. So this is the algorithm for skull stripping. This is a standard algorithm. So we have not done any contribution from our own side in this skull stripping algorithm. Normally this is the algorithm used for skull stripping. So now in this brain tissue, basically there are two parts, two types of tissues, non-cerebral tissues and cerebral tissues. So in non-cerebral tissues, skull portion, blood vessels and meninges, their average intensity levels are given. So based on this, a double thresholding algorithm is first employed to segregate the skull, blood vessels and meninges, and then we use the popular Otsu's thresholding algorithm to segregate the non-cerebral and cerebral tissues. So basically these three portions are removed, skull, blood vessels and meninges are removed, and the resulting image contains only the cerebral tissues. but we don't get very clean segmentation as such. So some morphological operations are required. So the morphological operations used are erosion, dilation, and region filling. So erosion is basically a thinning process. Dilation is thickening process. Erosion is followed by dilation, and then there are after this erosion and dilation, there are some holes remaining within the segmented area. So region filling is used to fill these holes, and after this morphological operations, we get the resultant image, which is a skull stripped image. So skull portion is removed. So you can see here in the diagram. So left one is the original image, and after skull stripping, you get an image where there is no skull portion. All the blood vessels are removed, and we can see only the white matter, gray matter, and the CSF portion in this skull stripped image. So these are the images used for segmentation. So this skull stripping is a pre-processing step that is required to be followed before segmentation. So we discussed basically two types of segmentation techniques. One is based on thresholding, and another is based on the clustering. So very basic clustering technique, the powerful clustering technique is a K-means clustering technique, or it is also known as C-means clustering technique. So it is an unsupervised technique for partitioning the data set. So this clustering, K-means clustering, basically clusters on the basis of high intra-class similarity and low inter-class similarity. So this is the algorithm in short. Our objective here is to say minimize this cost function. Okay. So in this K-means clustering, what we do is, suppose we have say n number of observations, or n number of pixels, or n number of data samples. Okay. We know how many clusters are there. So suppose there are c number of clusters. So arbitrarily we decide the cluster centers. So that is called as initialization of the cluster centers. So V1, V2, so on up to Vc are the initial cluster centers. These are arbitrarily decided, and then we try to say classify these n samples to these clusters V1 to Vc. Okay. So that is our first iteration. So how do we classify? Based on the distance. So xk are the data samples, and vi are the cluster centers. So we find the distance between these. Hello.
Mushrif sir. Actually, Dimay sir has logged in as a panelist, and from his side there was audio on by mistake. Which is, we have requested him to get off.
Okay.
Please continue.
Okay. So based on the Euclidean distance, these samples are allotted to the different cluster centers V1 to Vc, and after one iteration, the cluster centers are again recomputed. So, and this process is continued until there is no change in the cluster centers. So this is the basic K-means clustering algorithm. and so this is called as K-means clustering algorithm is called as hard clustering algorithm. Okay, so where the data sample belongs to any one cluster. So so modification of this clustering algorithm is called as fuzzy C-means clustering algorithm, where any sample is there is a graded membership of a sample to a cluster center now. So in hard clustering, the sample is either sample belongs to only one cluster, but in HCM, the sample belongs to the different clusters to a certain membership, which so okay. So we say that there is a fuzzy membership of a data sample to a cluster. Okay. So the objective function, which is to be minimized, is then modified as this. So there you can see one extra term here, mu ik. So mu ik is called as fuzzy partition matrix, which basically tell you about the membership of these the kth data element to ith cluster, and this P is the degree of fuzziness introduced. So P we can vary. Okay. So after every iteration, the partition matrix or membership matrix is modified according to this formula, and the cluster centers are also modified according to this formula. So these two formulae we obtain so as to minimize this objective function. Our aim is to minimize the objective function so that within class similarity is maximum and inter-class similarity is minimum. So that is the objective, okay, of the HCM algorithm. So this is the basic of HCM algorithm. So there are some drawbacks of this algorithm. This objective function does not take into account the spatial dependence among pixels in the image. So that is one thing, and membership function depends on the distance between kth sample and VIth center. So this membership function is sensitive to noise, and because of this we may not get good segmentation, especially when there is a high degree of noise and there is intensity homogeneity in MR images. So here two types of images are shown and their segmentation is shown. So these two images are segmented using the HCM algorithm. So in row 1, the original image is corrupted with 3% noise and 0% intensity homogeneity. So HCM is applied to this image, and the three segments are obtained. So CSF, gray matter and white matter. So you can see that because intensity homogeneity is 0%, you get fairly good segmentation. CSF, GM and gray matter and white matter are properly segmented. But in second image, the noise is 0%, but intensity in homogeneity is 40%. and the segmentation results are not that good. CSF is more or less properly segmented, but gray matter and white matter, these two portions are not segmented properly. Especially you can see the distortion in white matter. So that is the problem with the conventional HCM algorithm. So there are many variants of this HCM algorithm available. So there are literally say 15-20 variants available which have been tried on MRE basis. So one such variant is bias corrected HCM, which was proposed by Ahmad and all. And this algorithm deals with intensity inhomogeneity. So basically what it does is that while say classifying the data sample xk, it also takes into account the intensities of the pixels in its neighborhood. Okay. So immediate neighborhood pixels are also considered, and therefore the problem of intensity inhomogeneity is slightly reduced. So you can see that in the objective function there is one more term added. So this takes care of the intensity inhomogeneity. So basically this NR is the number of pixels in the neighborhood, and the neighborhood is denoted by NK. So this takes care of intensity inhomogeneity, and so this is a modified objective function, and this takes care of the intensity inhomogeneity. So, and there are many other variants available. I have just shown here one variant of HCM algorithm, which is known as bias corrected HCM, BCHCM. So we'll now discuss the thresholding algorithms. So one is fuzzy roughness measure based thresholding algorithm. So all of you are familiar with the thresholding algorithm, right? So a very popular algorithm, thresholding algorithm, is Otsu's thresholding algorithm, which minimizes the within class variance and maximizes the interclass variance. So based on this concept, this Otsu's algorithm is developed. Here we'll discuss two concepts rather than three concepts. One is histon, another is Roughness, and third one is fuzzy set. So I will discuss what is meant by histon first of all. So histon means histogram drawn on the top of another histogram. So I will just show you one histon diagram. So here you can see a graph, basically two graphs. One is called as histogram and another is known as histon. So this histon is another histon drawn on the top of the histogram, conventional histogram. So this histon again takes into account the similarity, takes into account the it is based on the similarity of the neighboring tissues. So I will discuss that. So histon is another histogram plotted on the top of the histogram. Okay. So this is how we calculate a conventional histogram. So it is basically a plot of say frequency of occurrence of intensities versus intensity. Right. So in order to compute histon, we consider a P by Q neighborhood around a pixel IMN, and we calculate these distances DTMN between the pixel at MNth position with its surrounding pixels in the neighborhood. So IPQ represents the pixel in the neighborhood and IMN represents the pixel at the center of the neighborhood. So for example, if it is a 3 by 3 neighborhood, then there will be 8 pixels surrounding this center pixel. So we calculate this distance as sum of these distances as DTMN. Right? And then we define a matrix which is of the same size as that of the image and call this matrix as XMN. This matrix is a binary matrix which basically contains ones and zeros. The element will be 1 if this distance DTMN is less than certain threshold, and the element will be 0 if the distance is greater than the certain threshold called as expanse. Okay. So what is expanse? Expanse is basically sum of all the distances of the distances between center pixel and the pixels in the neighborhood. That is called as expanse. So the idea is that this XMN MNF position, pixel at MNF position will be 1 when the center pixel is similar to its surrounding pixels. Okay. And while calculating the histogram, we take into account the value at corresponding position in the X matrix also. Okay. So this is the computation of histon, and so we get this type of graph which is called as histon. Okay. So now this histon is in computation of histon we use this matrix XMN, which is basically a binary matrix. So here we have to decide the value of expanse. So experimentally we can decide what is the best value of expanse, and accordingly this XMN can be calculated. Later on we modified this matrix and defined what is known as fuzzy histon. So in this fuzzy histon, this matrix is calculated using this Gaussian membership function. Okay. So where this sigma is the variance of the DTMN matrix. So we get instead of a binary matrix of the same size as image, we get a matrix where the values are in the range of 0 to 1. So this is called as a fuzzy Gaussian membership function. This is used for computation of histon. So it is called as fuzzy histon. Okay. So this membership mu mn is 1 if the center pixel is the intensity of the center pixel and the intensity value of the pixel in the neighborhood is exactly the same. In that case, this mu mn will be 1, and otherwise this mu mn will go on exponentially decaying. Okay. So here the advantage is that we need not define the expanse. So what is the advantage of using histon over the histogram? Because this histon takes into account the intensities of the surrounding pixels also. Okay, because it takes into account the intensities of the surrounding pixels also. The histogram, that is histon that we obtain, is well defined as compared to the conventional histogram. Now, well defined in the sense that the peak values and the value points that we get here are more meaningful. Suppose we want to do the segmentation, suppose we want to use a thresholding algorithm, simple thresholding algorithm to segment the image, then the threshold points are the threshold points are more well defined as compared to threshold points that we obtain in case of histogram, and therefore this results in a better segmentation. Okay. So that is the advantage of using the histon. Now further, so here we get basically two histograms. One is histogram, conventional histogram, and another histogram plotted on the top of the conventional histogram, which is known as histon. And there is a region between this histon and histogram. So we call this as rough region. Okay. So that also contains meaningful information, especially which will be useful for segmentation. So we use a rough set theoretic concept for defining what is known as roughness measure or roughness index. So basically, what is a rough set? It is a rough set it contains two crisp sets known as lower approximation and upper approximation. Okay, so rough set theory approximates rough or imprecise concepts by pair of exact concepts called as lower approximation and upper approximation. So without going into much details of the rough set theory, okay, we can say that this histogram, conventional histogram, represents the lower approximation and the histon represents the upper approximation. So these are the two sets that we get, and the region between these two is known as a rough region. So this histogram and histon are called as they are the crisp sets. So what does this histogram represent? So at any particular intensity value, what is the number of pixels which are having say these values? For example, intensity 100. So the value of the histogram at 100 represents that these are the number of intensities, number of pixels of intensity 100 in this image, and correspondingly what the histon value represents is it represents that these are the pixels in the image which are similar to the intensity 100. So that is the difference. Okay. So the histogram values represent the set of elements which definitely belong to that class, and histon values represent the elements which possibly belong to that class. Okay. So we define a measure known as roughness measure, which is defined as 1 minus the cardinality of this histon divided by the cardinality of histogram divided by the cardinality of the histon. Okay. So 1 minus f, small f g upon capital F g. So small f represents the histogram and capital F represents the histon. So this roughness measure, this index will be always this value will always be in the range of 0 to 1. Okay. So for all the intensities, say we'll get this roughness index value. So G represents the intensity values which vary from 0 to L minus 1. So we get an array in which these roughness index values are stored. So we can plot these roughness index versus intensities and we get this type of plot. So instead of using histogram or histon for thresholding, we can use this roughness measure versus intensity plot for thresholding. And here the valley points and the peak points are again more pronounced. They are, so we can say that this plot is more well defined for segmentation, more suited for segmentation. So we can use these valley points as threshold and segment the image. So segmentation result will be better as compared to segmentation obtained using histogram or using histon. Okay. So these are the results. So in the top row, the original image with 3% noise and 20% intensity inhomogeneity is shown. The second one in the top row is the ground truth image, and third one is the segmented image obtained using the algorithm that we just discussed. And in the second row, the segmentation results are the three different segments are shown: CSF, gray matter, and white matter. So you can see that gray matter, white matter are properly segmented, which we could not get in a simple, a conventional SCM algorithm. So we get a better segmentation using this algorithm. So we used several quantitative measures for deciding the quality of segmentation. So these quantitative measures use Jacquard similarity and size coefficient. So Jacquard similarity is defined as the ratio of cardinality of S1 intersection S2. So S1 represents the ground truth segmentation, and S2 represents the segmentation obtained by our method. So intersection of these two divided by the cardinality of the union of these two. So maximum value of Jacquard similarity will be 1 when the intersection and union represent the same set of pixels. Another index we use is a dice coefficient, or which is also called as overlap ratio. So it is calculated as 2 into the intersection of S1 and S2 divided by mod of S1 plus mod of S2. Again, this dice coefficient will also be equal to 1 when there is perfect segmentation, that is the number of the pixels in ground truth segmentation and pixels in the segmentation obtained using proposed method. They are identical. In that case, this dice coefficient will be 1. Otherwise, it will be in the range of 0 to 1. So these two quantitative measures are used to decide the quality of segmentation. So for various noise levels 0, 1, 3, 5, 7, 9%, and various intensity inhomogeneity 0, 20%, 40%, this Jacquard similarity and dice coefficients are calculated. So we observe that as the noise level increases, the values of the Jacquard similarity go on reducing. So when noise level is 0, the CSF and the inhomogeneity is 0%, CSF segmentation is 82% Jacquard similarity, whereas with 9% noise level, this Jacquard similarity reduces to 71.94%. Same thing happens with the other parameters also. Okay. So these are average Jacquard similarity and dice coefficient values for all the images in the set. So this is the confusion. We obtain confusion table also. For image with 5% noise and 20% inhomogeneity. So we found that the CSF true positive values are 82% for CSF, 93.59% for the gray matter, and 96.47% for the white matter. Then we also used this under segmentation, over segmentation, and incorrect segmentation indices for assessing the quality of segmentation. So under segmentation is the ratio of false positive to true negative. Over segmentation is the ratio of false negative to true positive. And incorrect segmentation is the ratio of sum of false positive and false negative to the total number of pixels in the segmented image. So again, for 1, 3, 5, 7% noise levels, we calculated these under segmentation, over segmentation, incorrect segmentation for CSF, gray matter and white matter, and we obtained these results. So as the noise level increases, this under segmentation index increases, over segmentation also increases, and so on. Then we introduced another algorithm known as intuitionistic fuzzy roughness measure algorithm, known as IFRM based thresholding algorithm. So along with the rough set theory, we also incorporated the intuitionistic fuzzy set theory also here. So what is an intuitionistic fuzzy set theory? We all are familiar with the fuzzy set theory, where the set A contains the set of elements X, which are having the membership values mu A. Okay. So there are two possibilities. Either this membership, sum of membership and non-membership will always be equal to 1. So if the membership value is say 0.7, so suppose particular element belongs to a particular set, so that belongingness is say up to the level of say 0.7, then automatically we can say that the non-membership value is 0.3. Okay, so there are only two possibilities. Either sum of membership plus non-membership will always be equal to 1. But in actual practice, that is not the case. Means membership plus non-membership will not always be equal to 1. So I will give you an example. Suppose somebody takes an opinion poll whether person A is suitable for his job or not. Okay, and suppose it is asked to say 1,000 persons. Then so, it may happen that 0.7% people will say that yes, he is suitable for this job, and there may be a 0.1% community which will say that he is not suitable for this job. So suitable plus not suitable is 0.9 only. So what about the other? So there is a third opinion also, which are so a set of people may say that we are undecided. We cannot decide whether a particular person is suitable for this job or not. So we say that they are hesitant. Okay. So there is a third parameter called as hesitance also. So a membership, non-membership, and hesitation. So these are the three possibilities, right? So in intuitionistic fuzzy-set theory, three types of memberships are considered. One is membership, another is non-membership, and third parameter is the degree of hesitation. Okay. So now in images also this kind of hesitancy may exist, particularly among the boundary pixels. So boundary between the two objects or two segments in an image is never this cannot be can never be described in a crisp way, whether the particular pixel belongs to segment A or segment B. We cannot tell precisely. So if we use a fuzzy set theory, we may say that this belongs to segment A to the degree of say 0.6. It automatically means that it doesn't belong to a degree of 0.4, right? But that is not the case. Okay, so there is a hesitation. One may say that our say algorithm may not be conclusive that the pixel belongs to segment A or segment B. So there is a degree of hesitation, and if that is exploited, that is also taken into account by the algorithm, then the segmentation accuracy improves. So this third parameter is known as intuitionistic fuzzy index or hesitancy degree, and this concept we have applied in our thresholding algorithm. So now the membership plus non-membership plus hesitancy will always be equal to 1. Okay. So that is the basic concept of intuitionistic fuzzy set. So we can define an image as an intuitionistic fuzzy image where the image I can be represented with 3 now matrices. Each element will have 3 portions. One is fuzzy, one is a membership value to that particular intensity. Another one is non-membership value, and third one will be the hesitancy. Okay. So we evaluate the membership value simply by dividing the intensity value of pixel at ij location by L minus 1, where L is the maximum intensity. Okay. So if it is a 8-bit image, then we'll divide every element by 255. So we'll get the values in the range of 0 to 1. So we call these as say membership values, and to compute non-membership value, we used a Sugino fuzzy complement. It is defined by this formula. So that will decide the non-membership value. So non-membership degree is calculated using this Sugino fuzzy complement, and then the hesitation degree is computed by subtracting membership plus non-membership from 1. That will give the hesitancy degree. And then we define the histon, intuitionistic fuzzy histon, and calculate the intuitionistic fuzzy roughness index. So while calculating this intuitionistic fuzzy roughness index, we have assumed that the image is an IFS image, intuitionistic fuzzy image. Okay. So using this concept, we calculated the histon. So this matrix mu mn is now a matrix which contains basically the 3 elements. Okay. So the distance formula is also modified accordingly. Okay. So this is intuitionistic fuzzy distance between the 2 pixels at locations mn and eq. So this is basically a Euclidean distance, but considering the membership, non-membership, and hesitancy values. So we get these plots: fuzzy roughness, intuitionistic fuzzy roughness index versus intensity value. And now this plot, this graph is now more well defined. We get precise threshold and precise value and peak points. So value points are used as the thresholds for segmenting, and then we get these results. Okay. So original image with 5% noise, 40% inhomogeneity. This is the ground truth image. Third one is the segmented image, and then these are the 3 segments: CSF, gray matter, and white matter. These are few more segmentation results with 5% noise and varying intensity inhomogeneity. So 0% intensity inhomogeneity, 20%, 40%, and 60%, and their corresponding segmentation results. Then we have done the quantitative analysis also for this. We calculated the Jacquard similarity index and type coefficient index for all this for different noise levels and different intensities. So we find that as the noise level increases and as the intensity inhomogeneity increases, the index values, the quality of segmentation also gets reduced. Okay. So these are the confusion tables. Then under segmentation, over segmentation, and incorrect segmentation values. So again, we find that as the noise level increases, the under segmentation, over segmentation, incorrect segmentation percentages also increase for all CSF, gray matter, and white matter. So if we compare these results with compare the results of fuzzy roughness measure based thresholding and intuitionistic fuzzy roughness based thresholding, then we observe that the segmentation performance is slightly better. Okay, here you can observe. For FRM, this is 91%. IFRM, this value is 92%. So in every respect, you can observe that we get a better segmentation if we use intuitionistic fuzzy roughness based technique. Then the results are also compared with the modified FCM. So we find that intuitionistic fuzzy roughness based thresholding gives slightly better results as compared to the modified FCM method. This is suggested by one of the researchers, which is mentioned in the reference 9 here. So this comparison also shows that the IFRM is better as far as gray matter segmentation is concerned. For white matter, for say intensity inhomogeneity of 3%, the IFRM method does not give better results, but in other cases the results are good. So these are few more comparisons. Then we applied these rough set theoretic concepts and intuitionistic fuzzy set theoretic concepts to the clustering algorithms, that is FCM. So this is the standard FCM which we have discussed earlier. And this is the so we used intuitionistic fuzzy sequence algorithm. So where the only difference is that this distance is calculated. This distance is now IFS distance, which takes into account the membership values, non-membership values, and the hesitancy degree also. And then these partition matrix, that is membership matrix, and the cluster centers are modified after every iteration, which take into account or which in which the distances are now the intuitionistic fuzzy distances. So these results we obtain for the images with 3% noise and 20% inhomogeneity. So again, the original image, ground truth image, and the segmented image. Okay. The second row shows the IFS rough region of CSF, gray matter and white matter, and third row basically shows the segmentation using the proposed algorithm. So if we do the visual comparison or qualitative comparison, then it is difficult to make out any difference between these segmentations. But if we use, say, quantitative analysis, then we can see the improvements in the results by this intuitionistic fuzzy clustering algorithm. So the results are compared with ECFCM, bias corrected FCM, with the IFS clustering algorithm, and this is a roughness index based FCM algorithm. So we get better results using IFS or RIFCM algorithm as compared to BCFCM. Then dice coefficients and dice coefficients are calculated for BCFCM, IFS clustering, and RIFCM. So these are the results. confusion tables, and then under segmentation, over segmentation, incorrect segmentations are evaluated. Then we also compared the results of RIFCM with NLRFCM. NLRFCM stands for the non-local FCM, which is proposed by some researcher. So with that we have compared our algorithm. So we find that the gray matter and white matter segmentations are better as compared to the method that is compared with the algorithm presented in the literature. So these are the comparisons with several other algorithms. So we find that RIFCM gives the better results. Then for say computation of anti-synergistic fuzzy membership values, earlier we discussed that we use the Sugino fuzzy complement. We also defined our own complement for calculating the non-membership value. So we defined our own complement function as 1 minus membership value into exponential of the minus of membership value divided by a into the standard deviation of membership value raised to 1 by a. So this a is a fuzzification factor. So we defined our own fuzzy complement and used it and compared with the Sugino fuzzy complement and Jaeger's intuitionistic fuzzy complement, and we observed that we got better results in many cases using our own fuzzy complement technique. Okay, so comparison with the Jaeger's fuzzy complement and Sugino fuzzy complement methods are also given. So we observe that our fuzzy complement technique is a better one. So there are many results to show, but I think the time is over. So I will stop here. If there are any questions, I can answer the questions.
Yeah, thank you, Mushrif sir.
Yeah.
Well, participants, session is over from Mushrif sir's end. You can go with your questions if you have. You can put up your questions in question answer box or maybe in chat box also. Sir, we will wait for 1 or 2 minutes.
Okay.
But I mean, it takes some time for participants to put up the questions.
Okay.
Yeah, there is a question, sir. Hello, sir. Mushrif sir. Where from we get the ground truth images?
Ground truth images, I mentioned that we obtain those brainwave images. We'll show the reference. It is there. Yeah, first reference. www.bic.mni.mcgil.ca/brainwave. These are basically simulated images, not the real images, but these images are ground truth images, very useful for say analyzing the performance of your segmentation techniques, because say images right from 0%, 1% noise to 0% noise to 9% noise, and various intensity inhomogeneities are available there. So you can consider those as benchmark images and compare your results with them.
Okay. Yeah, participants, any more questions? No. Yeah. In biomedical image processing, what are the performance parameters? Is it always a specificity, sensitivity with the use of PN, PP, FN and FP?
You can find many performance measures in the literature. So some of them I have used here, and other than this, people have used RAND index, then many other performance measures you can see. I have also used RAND index, which is also a good performance measure for comparing your results. No, I'm not finding any question. Yeah. Sir, one more question is there. Can you throw some light on other potential applications in MRI image processing? Other potential applications.
Yeah.
See, we have basically discussed these segmentation algorithms and one classification algorithm. But after segmentation, you can say go for the detection of tumors, and then classification of those tumors are say benign tumors or malignant tumors. If the tumors are malignant, then grading, you can go for the analysis of grading of these malignant tumors as stage 1, stage 2 and so on. Other than this, you can also do research on say diseases like Alzheimer's or some other diseases like that. So a lot of research is going on these images. Segmentation is, you can say that it is just a pre-processing step for doing further analysis. So a lot of scope is there, and a lot of research work is also going on.
Yeah, it seems questions are over.
Okay.
We can end up from our end also. Well, dear participants, that was a session by Dr. Mushrif. He took you through basics of brain images first. I mean, as gentle as he is, he first of all touched upon basics of brain images, and then the journey started towards segmentation. Further moved on to FCM basics, then bias corrected FCM. Then again, what he presented in the form of fuzzy roughness measure histon, then under segmentation, over segmentation, and incorrect segmentation for the quality of segmentation that particularly researchers looks into. Further, he provided the comparisons of this FCM, FRM, and then intuitionistic fuzzy set theory and algorithms with roughness of this segmentation and images, and so on. So that was a nice session by Dr. Mushrif sir as far as the applications of image processing in the biomedical field is concerned. On behalf of all of us, sir, we are very much thankful to you for providing insight into brain MRI image data analysis, and definitely the inputs that you have provided in your session will be helpful for all the participants to take their research in the respective areas to the next level. And of course, as these activities are basically with the objectives of imparting to these first areas to the students, definitely the knowledge across the participants from the across the country will definitely impart the inputs that are there that they have gained to this session to their students at their respective institutes. Thank you very much, sir.
Okay. Thank you, Khanapurkar sir and Akant madam for giving me opportunity to give a lecture in your session. Thank you all participants, and in case you have any query or anything, you can contact me in future also. Thank you very much.
Sir, one query there from one participant. We'll take up.
Yeah.
Please permit me. Yeah. It goes like this. Professor Mamta is asking, which is good denoising algorithm to remove speckle noise in MR images?
For removing speckle noise, just a minute. So in my one of the slides I have told you about. So there are many denoising algorithms, so you can design some specific filters, or there are some diffusion based anisotropic diffusion based filtering techniques which can be used for denoising. Okay. So I hope I have answered the question.
Yeah. Thank you, sir.
Okay. Thank you. Thank you, sir, very much.
Well, dear participants, day 4 session 1 is over. We will take a 10 minutes health break. By the time next session will be ready, and I request all of you to join or be in the session. Don't get yourself log off. We are keeping session on. For the next session, we are about to start maybe within 5-6 minutes. I would like to make an important announcement here, which I have posted on in WhatsApp group. We have a little change in the schedule as far as today's rest of the sessions are concerned. Session 2 and session 3 are swapped. I am again repeating, session 2 and session 3 are swapped. But again, keep in mind and let us this thing. The timings are unchanged. Link is also unchanged. This is because from at our end, at a respective experts end, there were some issues like this thing. So session 3 today, which was scheduled and which was informed to you, which was by Dr. Prof. He will be taking the session 3 right now. That is as a session 2, and vice versa. That means session 2 will be shifted to as session 3. That will be there. So kindly take a note of this. Again, I am again repeating. Link remains same. Don't log off. Then timing remains same. We are about to start. It is 11:40. We will start within 5-6 minutes as Dr. Swagat Chitna from VNIT joins in, and then the scheduled session 2 will be taken up as session 3. Thank you very much. Take a health break for 5 minutes and stay logged in and we'll start within as earlier possible. Thank you.